scene opens with a stunning cinematic visual of a massive, glowing blue star being violently shredded. Tendrils of stellar gas are pulled away, spiraling into the glowing chaotic accretion disk surrounding a black hole. The scene is dramatic and terrifyingly beautiful. The sound is a low, deep rumble. What if I told you there are objects in space so powerful, so dense, that they break the very laws of physics as we know them? Monsters of gravity so extreme that not even light, the fastest thing in the universe, can escape their grasp. Imagine a cosmic abyss where time itself stretches and slows, where the fabric of reality is warped beyond recognition, and where stars, entire solar systems, can simply vanish without a trace. These aren't just concepts from science fiction. They are a fundamental and terrifying part of our cosmos. These are black holes, transitioned to a smooth animation of a massive star, many times larger than our sun, burning with intense blue-white light against the backdrop of a nebula. To understand these cosmic enigmas, we must first witness a birth forged in cosmic violence. It all begins with a star, a true giant at least 20 times more massive than our own sun. For millions of years, this stellar behemoth burns through its fuel, a delicate balance between the outward push of nuclear fusion in its core and the inward crush of its own immense gravity. But this cosmic balancing act cannot last forever. When the star exhausts its fuel, the furnace at its heart sputters and dies. Gravity, relentless and unopposed, wins the final battle. The animated star swells dramatically into a bloated red supergiant. Then, in a brilliant flash, it collapses in on itself and explodes in a spectacular supernova. The outer layers are blasted into space while the core continues to shrink. In a fraction of a second, the core collapses under its own weight, imploding with unimaginable force. The outer layers are thrown off in one of the most brilliant events in the universe, a supernova explosion that can outshine an entire galaxy. But what remains of the core is the seed of something far stranger. It continues to collapse, crushing matter down to a point of infinite density and zero volume, a place where our understanding of physics completely breaks down. This is the singularity. The gravitational pull of this tiny, impossibly massive point is so strong that it punches a hole in the fabric of space-time itself, creating the abyss we call a black hole. The scene shifts to a stylized historical segment. An animated portrait of Albert Einstein appears, with chalk-like equations floating around him. An animation shows a flat rubber sheet representing space-time. But how did we even begin to conceive of such an object? Our journey into darkness begins not with a telescope, but with the mind of one of humanity's greatest thinkers, Albert Einstein. In 1915, his theory of general relativity revolutionized our understanding of gravity. He proposed that massive objects don't just pull on other objects, they fundamentally bend and warp the very fabric of space-time around them. Imagine a bowling ball placed on a rubber sheet. Its weight creates a dip, and other, smaller objects are forced to roll towards it. This is gravity. An old-fashioned photo of Carl Schwarzschild appears. The rubber sheet animation now shows the bowling ball being replaced by an infinitely heavy, tiny point, creating a bottomless well in the sheet. A distinct line forms around the well. Einstein's equations were notoriously complex, but just a year later, a German physicist named Carl Schwarzschild found a solution while serving on the front lines of World War I. He calculated that if you could compress enough mass into a small enough space, the curvature of space-time would become infinite. His equations described a boundary around this singularity, a line of no return from which nothing could escape. We now call this the Schwarzschild radius, or more famously, the event horizon. The scene transitions to a more modern, digital animation. We see Stephen Hawking in his wheelchair, looking up at a starry sky. An animation shows a black hole with pairs of virtual particles popping into existence near the event horizon. One falls in, the other escapes. For decades, black holes remained a mathematical curiosity, but the story doesn't end there. In the 1970s, Stephen Hawking made a groundbreaking discovery that defied everything we thought we knew. By combining quantum mechanics with general relativity, he theorized that black holes are not entirely black. He proposed that over immense timescales, they can slowly leak energy and evaporate. This phenomenon, known as Hawking radiation, suggests that even the most eternal objects in the universe have a finite lifespan, slowly fading away over trillions upon trillions of years. The camera dramatically zooms toward the event horizon of a supermassive black hole. The accretion disk swirls violently and the darkness in the center is absolute. The narrator's voice becomes a low whisper. We've learned what they are and who first dared to imagine them. But what different kinds of black holes lurk in the dark corners of our universe? And what would truly happen if you were to fall past the point of no return? Join us in part 2 as we take the ultimate plunge and journey beyond the event horizon.